Hello, thanks for coming to my Flash Talk. My name is Paul Bloom, and I'll be talking about a project investigating age-related change in amygdala-prefrontal circuitry using task-based fMRI with a longitudinal dataset and multiverse analysis approaches. I've been doing this work as a PhD student in Nim Tottenham's lab at Columbia University, and also in collaboration with Miriam Ali. For this project, our main objective was to understand within-person changes over time in task-elicited amygdala MPFC, or medial prefrontal cortex, circuitry between the ages of 4 and 22 years. Secondly, given that recent work has highlighted how different analysis choices can influence imaging results, we wanted to assess whether results on age-related change are robust to analysis decision points. We used multiverse analyses to do this. So for this study, we conducted secondary data analyses on a longitudinal cohort studied from 2009 to 2015. It was recruited from around the greater LA area through flyers, state birth records, community events, psychologist offices, online ads, and word of mouth. The study had 3 longitudinal waves spaced about 18 months apart each, and recruitment was done mostly at the first time point, but some participants were recruited at wave 2 as well. For our project, we included all participants with at least one scan with sufficient quality data for analysis. We did have to exclude a fairly large number of scans in this quality assurance process. In addition, while the sample was fairly heterogeneous in terms of race, this cohort was not sampled to represent the LA or United States population in an epidemiological sense. So for our analyses, we wound up with a dataset of 98 participants aged 4 to 22 and a total N of 183 scans for analysis. Not everyone completed all 3 scans, but we did include participants with at least one usable scan to maximize our power. In the scanner, each participant completed an emotion discrimination task with an event-related design. Faces appeared on the screen for 350 milliseconds each, and participants were instructed to press for neutral faces and to withhold button presses for fearful faces. We had 2 a priori hypotheses for this project. First, we predicted that there would be decreases in amygdala reactivity to the fear faces with increasing age. Secondly, we predicted there would be decreases in amygdala MPFC functional connectivity with increasing age, such that there would be a developmental shift from positive to negative connectivity, as measured with a generalized psychophysiological interaction, or GPPI model. We did pre-register these analyses on the Open Science Framework, but I do want to be clear that in our journey with this project, we did many more things beyond what we pre-registered. In our analysis approach, we really wanted to examine whether our results would be robust across many of the analysis decisions that we could take. So, with our multiverse, we generated all of the reasonable analyses pipelines that we could think of across many levels of decisions, then conducted as many of them in parallel as possible. If you'd like to know more about the analysis pipelines we used, please come talk to me about it. When we looked at our amygdala reactivity results, most of them looked similar to this graph. Here we have age on the x-axis and estimated amygdala reactivity to faces on the y-axis. While there was a lot of variability, in general, we see higher amygdala reactivity on average earlier in development and decreases with age for both the fear and neutral faces. However, this graph only represents one pipeline out of about 2,800 that we ran. This one had the median slope with regards to age. So we can contextualize that median pipeline within the results from all pipelines together in a specification curve, where our x-axis represents all 2,800 pipelines ranked by the magnitude of the estimated age-related change or slope, which is represented on the y-axis. We found that 60% of them in red indicated negative age-related change in amygdala reactivity to the fear faces with a confidence interval excluding 0. So for these pipelines, we might conclude that there is a significant decrease in amygdala reactivity with age. However, for the other 40% of the pipelines in blue and green, we might conclude that there isn't any consistent age-related change in amygdala reactivity, even though the vast majority indicate numerically negative change. So, while the results are consistent in sign across pipelines here, there is substantial variability, and different sets of analysis choices could lead us to qualitatively different conclusions. With our analyses of amygdala MPFC functional connectivity using GPPI, we actually saw even more variability in the estimated age-related change. While some pipelines found positive age-related change with confidence intervals excluding 0, represented in the purple, overall we don't see much evidence of any robust age-related change here, either positive or negative. For our GPPI functional connectivity analyses, I want to mention that in particular, these results were extremely sensitive to whether or not we included a deconvolution step when creating the GPPI regressors. I don't have time to go into this detail right now, but please feel free to ask me about this later if you're interested. In addition to the GPPI analyses, we also examined amygdala MPFC functional connectivity using beta series correlation analyses, and with these we similarly found no evidence for robust age-related change across our pipelines. So, in conclusion, our results are in agreement with prior work indicating that neuroimaging findings can be highly sensitive to analysis methods. In this respect, we find that multiverse analyses are super useful for determining the robustness of findings and for understanding which decision points influence our findings the most. In terms of development, we do find some evidence for age-related decreases in amygdala reactivity to both fearful and neutral faces across our pipelines. However, we don't see any evidence for age-related change in amygdala MPFC functional connectivity. With our results, we recognize a few main caveats. First, that we don't see any evidence for age-related change does not mean that we have strong evidence against there being age-related change. For functional connectivity analyses in particular, we do not find consistent estimates where the slopes were precisely estimated near zero. So for now, the most that we can say is that we don't have any evidence for age-related change in those analyses, but we aren't ruling out the possibility that such effects could exist beyond what we were able to estimate here. In addition, our sample was not representative of the US population, especially in terms of socioeconomic status, so epidemiological strategies for representative sampling could stand to influence our results. Finally, the strength of our conclusions are limited by our relatively small sample size, as well as the fact that scans were relatively short, about 4.5 minutes, and that we used a rapid event-related task design. In particular, this design may have made it difficult to get reliable estimates of functional connectivity for our GPPI analyses. Lastly, thank you so much for coming to this talk. I want to give an extra thanks to my advisors Nim Tottenham and Miriam Ali, and all of my collaborators for their mentorship and support in this project. A big thank you to the lab, our participating families, and of course, thanks to SRCD for the chance to present this work here. If you have any questions, feedback, or comments, please come and find me. I'd love to talk to you more about this project.